Happy New Year, everyone. Welcome to the second half of our seminar for this year. I hope everyone had a good sort of holiday time. Our speaker today is Louis Marin from the Université Gustave Eiffel, although he is in Montreal right now for the holidays. He will speak to us about maximal two-dimensional binary words of bounded degree.
All right. Well, thank you everyone for coming after the holidays, and also a happy New Year's, everyone. Happy New Year, everyone. So I'm going to talk to you about two-dimensional words. So I don't know what everyone's familiarity with two-dimensional words is. Thankfully, for this project, you won't need to have that deep of an understanding of the very deep theory on two-dimensional words. We'll keep it at the basic level. We won't need that much heavy theory. And this work is joint work with Alexandre Londemassé, Alain Goupil, and Raphaël. All right, so first, what's the framework of the problem? So we have a finite alphabet. So here we'll work on the binary alphabet, comprised of those two letters. So the first letter we call the empty cell, and the other letter we'll call either the full cell or the occupied cell interchangeably. So what's a two-dimensional word? Well, first of all, we have a height and a width. And a two-dimensional word in this alphabet is simply a matrix with entries in this alphabet. And the matrix will have these dimensions, this height and this width. For a bit of notation, we'll call Wij is simply the entry of the word W at row I in column J. And what we'll call the neighborhood of an entry in W are the entries that are directly to, basically, its left, its north, its here it's left, it's right, it's south, and it's north, basically, if they exist. If an entry is at let's say, a corner of the word, then its neighborhood will comprise of only two other entries, or letters, for short. We'll introduce the notion of degree for in a two-dimensional word with this alphabet. We only look at the degree of an entry if the letter is the occupied cell letter, and its degree is simply the number of other occupied cells in this neighborhood. So the neighborhood does not include itself. So an entry is not part of its neighborhood, and the neighborhood of the cell is the number of occupied cell in its neighborhood. The degree of the cell. And now, so basically the problem we want to look at is we want to limit we want to look at words such that for no entry, for no occupied cell entry in the word, there is no cell that has degree greater than D for a fixed D. So those are the objects we want to look at in this problem. And I guess we can introduce also this statistic, which is just the number of, so this notation is just the number of occupied cells in the word W, and this is just the number of unoccupied cells in the word W. Also, sometimes, since this problem can also be seen as a discrete geometry problem, we call this statistic the number of occupied cells in a word. We can call it the area of a word. So now the goal is basically we fix a number D, basically a maximal number of cells in a maximal degree, basically. We fix a maximal degree, and we want to look at the maximal area of a word that respects the condition that none of its occupied cell has degree greater than D. this is the goal of of today's talk. So yeah, so basically for all triplets, D, H, and W, so D being the degree and H and W being the dimensions of the word, we want to find all so we want to find automatically the value of the maximal area of a word that has those three parameters. Yes, and also this problem is entirely symmetric with regard to H and W, of course. So, for example, those are examples of words 7, like of word 7 by 4 for each degree D. So this is an example of D equals 0, D equals 1, D equals 2, D equals 3, and D equals 4. So first, what we can, well, I mean, so maybe we could talk about where this problem comes from. So at first, because I mean, the problem for D equals 4 is totally obvious. Like it's not really a problem, but for the sake of completeness, we put it there just for being exhaustive. Also, the problem for D equals 0 and D equals 1 are, well, I mean, they've been solved already, and they are actually pretty obvious. We'll talk a bit about them, but they're pretty obvious. And the problem for D equals 3 actually can be derived from a quite recent paper on dominating sets on graphs. I'll explain it. I'll explain everything later on the talk. But mainly, what we were focused in was trying to solve this problem for D equals 2, which was like it's which matched in hardness, let's say, the case for D equals 3. So most of the talk will be talking about the D equals 2 case. And under a bit of notation, we say that a word is D full if it is a maximal word with those three parameters, a maximal area word with those three parameters. We say that it's D full. So let's say that this word is 0 full, this word is 2 full, etc. All right, so why words? Like, why would we frame this problem as a problem on combinatorics on words? Because actually, this problem can be seen like as a problem in like combinatorics, like a problem on polyominoes or forest of polyominoes. It could also be seen, and we'll see this later, as a problem of graph theory, like of dominating set. It can be seen basically as a generalization of the dominating set problem. But we chose to use we found that the word theory was the most natural framing because we used a lot of its notation and tools. Like it's useful to see parts of the words as factors, and also it can be seen as a pattern avoidance problem, which is common on combinatorics on words. Like for the D equals 0 case, we want to avoid this pattern. For the D equals 2 case, we want to avoid all those patterns, etc. All right, so for two-dimensional words, we have two basic operations, which are the horizontal concatenation and vertical concatenation. And why are those? I mean, so maybe the particularity that 2D words have over, I mean, or maybe even under 1D word is that, so for horizontal concatenation, for our definition, it can only exist if two words share the same height. Like two words can be horizontally concatenated only if they have the same height. Which means that this operation is not closed. Like the set is not closed under this operation. Same thing for vertical concatenation. We need both concatenated words to be of the same width. Otherwise, this operation does not exist between two words that don't have the same width. So the set of 2D words is not closed under either of those operations. So maybe that's why. So maybe that's a particularity that 2D words don't have that 1D words have. Maybe they're a bit less interesting in the algebraic sense. I don't know. So, but this is the notation we will use. And for the exponentiation, we actually when we the power of a word has to be well, we need to specify two parameters when we take the power of a word. So the first parameter is its power vertically. How many times do you concatenate it vertically? And the other power is and the other number is the number of times you concatenate it horizontally. And if you do it with a fraction, it just means that. So let's say here it's 7/3. Basically, you concatenate it two times and a third. So basically, the first column. So this is what you get when you take this word to this power. All right, so maybe we can look at the easy cases, like I said. So, well, first of all, maybe the case d equals 2. I mean, we won't look at d equals 4 because it's nothing. So d equals 2. I mean, so the result is simply that it's the half. It's simply that it's half of the word that can be filled with squares. And the proof is just by pigeonhole principle. It's quite easy to come up with. It's quite easy to come up with example that reaches this area. But now if you want to prove that it's maximal, we just need to separate the square into dominoes. And depending on the parity of the height and the width, sometimes we can separate it in dominoes and one monomial, which is the case here and on the right. And in this case, then we will have one more than, I mean, we would have half of the square rounded up, having an occupied cell. So this is one of the easy example. The other easy example, which is pretty much the same thing, is for d equals 1. So it's a bit more elaborate maybe, but it's just amounts to the same idea that we can always reach those. So those are the values of maximal area, and you can see that they depend on the parity of h and w. But for each of those cases, it's just okay. Well, how can we tile the rectangle with squares? And for each square, we know that there can be at most two occupied cells. But sometimes, if depending on the parity, we can we have a leftover band that we can tile with 3x1s and 2x1s. And those, I mean, the 3x1s, they can have two cells, at most two cells, and the 2x1s also can have at most two cells. And that's how we reach that's how you can you can reach those those numbers that have slightly more, like a ratio of slightly more occupied cells than this ratio. All right, and now maybe we can maybe I've did a bit of a spoiler already, but we will talk a bit about dominating sets, which will be important for the d equals 3 case. So what's a dominating set? So let's say we have a graph. We say that a subset of vertices is a dominating set if for each vertex in the graph, either a vertex is in the set or touches the set. So here in green, so this is an example, here in green, we have a dominating set. Why? Because either each vertex is in the set or it touches each vertex touches at least one vertex in the dominating set. And so we say that the dominating set is minimal if there is no dominating set with less vertices, which so basically we want to find basically what is the dominating set with the least amount of vertices in it. I mean, because finding a dominating set is very easy. You can just, like, if you don't care about the minimality, you can just select every vertex to be in your dominating set and you win, but it's not very interesting. So here the idea is to find the minimal one. And the cardinality of the minimal dominating set is called the domination number. And this is basically a known problem, a very hard problem. Finding the dominating number of a graph is known to be very hard. But thankfully, like I said earlier, a recent article has solved it for the case of the grid graph, and we will see how this could be used for us. So we'll try to use a dominating set to construct a threefold word. So how do we do it? Well, first we start with just a word that is filled with occupied cells. Now, obviously, this word is not threefold because it does not respect the condition that no occupied cell has a neighborhood of 4. Now, what we can do is we can look at the cells inside that are not in the border of your word, and for each cell we link it with a cell in its neighborhood that is like vertices basically adjacent to in order to get a grid graph. Now, if we can find a dominating set of this grid graph, what we could do is then for each cell in the dominating cell, we can remove this cell, and this will give us a threefold word. Why? Well, because when so basically what we want is for none of the occupied cells to have a neighborhood of 4. So we basically all they have to do is for each. So it's impossible basically. So first of all, it's impossible for a cell in the border to not comply to this restriction because their neighborhood is less than 4. So they already all comply to this rule. But the interior cell, the cells that are not in the border, what they need is they all need to touch at least one empty cell. And how we can guarantee that is that each cell. So I mean, basically, that's the definition of a dominating set. Either you're in the set or you touch a cell in, or you touch a vertex in the set. So if we remove every interior cell in your dominating set, you get a threefold word. So yeah, so basically, what's the maximal area of a threefold word? Well, if every cell is in the border, then there's no problem. You get the full area, but otherwise you get the full area minus the dominating number of the grid graph that is of the grid graph that is the size of the interior of your word. And like I said, thankfully this problem was solved in 2011 by Gonçalves, Painlu, Rao, and Tomase. The way they solved it was mainly using computer programs based on dynamic programming. It was a lot of case checking and like hard computations. And what this suggests is that maybe for those kind of problems, it's hard to come up with an elegant proof. And we're not saying that it's not possible, but so at first maybe when we tackled this problem at first and we found this article, we had already and I mean I guess I'm gonna show it to you right away, but we were already deep into case checking and like a brutal combinatorial proofs. Going case by case, and we were trying to find a unified proofs, but maybe seeing this article, we were like, okay, well, maybe it's harder than it looks to find a beautiful proof of this result. But maybe I want to talk a bit about how the problem for any D could be also seen as a dominating set problem. So very quickly, so we've seen that that the definition of a dominating set is that so for a graph G, any vertex is either in the set or touches one of the vertex in the set. Well, and we use this fact to construct a three-fold word. But maybe how could we use this fact to construct a two-fold word, or even a one-fold word, or a zero-fold word? Well, if instead of only looking, so the dominating set is defined as, like I said, either you are in the set or you touch one vertex in the set. If we instead define it as either you're in the set or you touch at least two vertex in the dominating set, then in a similar way, we could construct a two-fold word. And if we extend it to maybe, okay, so this is just, so this is for d equals 2. For d equals 1, it could be that you look at the dominating set, which such that like maybe a third degree dominating set, which means that you're either in the set or you touch at least three vertex in the set. This could be a way to construct also a one-fold word. And so basically it's just like a way to see that that this problem can also be seen as like a generalization of the generating the dominating set problem. All right, so maybe let's tackle the big one. So d equals 2. So here's a table of the maximal area of basically of two full words with this width and this height with and yeah, so I mean, so right now it's not really eloquent. I mean, obviously it's symmetric, but there's not much we can very infer looking at just this table. But let's say, but we can introduce this statistic, which we call the excess. And what does it do is basically you take the area of your word, and you subtract to it 2/3 of the area of the area, basically 2/3 of the number of letters, basically. So you look at the ratio of how many of your letters are occupied cells compared to 2/3 of the word. And we denote, and we say that the maximal excess of a dimension HW is simply the excess of the maximal of a two-fold word of dimension H and W. Well, if you do this and you look at the table, well, maybe some patterns start to pop up. Like first of all, well, we can see that for 3, for one of the dimensions being equal to 3, we can see that after a while, after reaching 3, it stays at 2. The excess is continually at 2. And for the other, like for the dimensions higher, we can see that we have like a periodicity in the excess, which means that this square, it repeats itself indefinitely. For the the dimensions, for the cases in which one of the dimensions is 1, and in the cases for which one of the dimensions is 2, then maybe it's not too clear that there's a pattern there. Maybe, I mean, because it keeps on growing. So the excess here it might not be as adapted for those cases. But for the case where one of the dimensions is 3 and higher, then excess seems to be a statistic that is important to keep in mind. So we'll try to use this to prove, to find basically the maximal area of two-fold words for any dimension. And also, yeah, of course, up to symmetry, we can remove those cases because they're the same as those 3 cases. So basically, for the cases, for the cases where the dimension, both of the dimensions are large, there's only 6 cases to check up to symmetry. So those are the 6 cases. But we also need to, of course, take care of the cases where one of the dimensions is a bit lower. Also, yeah, I guess it's important to say that whenever you concatenate either horizontally or vertically two words, you're not guaranteed to keep having full words, but I mean we can define excess on any not just two words. So excess can be defined for any words basically. But what is important to notice is that whenever you add or concatenate two words with a certain excess, then both of their excess add up, which is a fact we will use. It's not too hard to convince yourself. Maybe a 3-second thought, and you'll be convinced. Yes, and also this is a notation. All right. So we will proceed by induction, but we need to take care of the base cases first. And actually, there's a lot of base cases. So there's the case where one of the dimensions is one of the dimensions is two, one of the dimensions is 3, 4, 5, 6, and the other dimension can be arbitrarily large. And there's also the case where the case 7 by 7 that we need to check. And after all of these cases will be checked, we can use them to proceed by induction. All right, so for the case 1 by n, 1 by h, basically, basically we can just notice that it's impossible for a word. We can fill basically a 1 by h word. We can always fill it with occupied cells, and it can never contain a cell with neighborhood of 3 because every cell is in a strip. Basically, they don't have east or west neighbors. So that also explains why the excess in the one line is not bounded, because we can always fill it with squares. And for the case where one of the dimensions is 2, well, we can fill it in this way, which I mean, we need to prove that it's maximal, but it's not too hard. And this we can see that when we separate it in blocks of 4, you can see that it's actually 3/4 of the area that is occupied by occupied cells. So that also explains why in this table, the excess seems to be unbounded, because the good ratio for 2 is actually 3/4. It's not 2/3. All right, so those were the easy cases. So maybe I can sketch a little bit how we can prove the other base cases. I'll do for the base case W equals 3. The other base cases we proceeded similarly, but each time with increasing amounts of cases to check and like some small lemmas to obtain the result. But the basic philosophy, we'll see it with the case W equals 3. And so remember that for one of the dimensions be equal to 3, that the excess was equal to 2. Okay, we had this over here, so we know that a two full word, of h by 3 will always have excess 2. So, but it's easy to obtain a word of excess 2 with 3. This is an example of how you could do it. You could simply fill the bottom row, fill the top row, and all the middle rows we can fill them with this pattern, like occupied, empty, occupied. This will give us a cycle, like a long cycle, which will be twofold. Like none of those cells will be of degree more than 2, and it would be of excess 2 because every middle row is of excess 0, and the top and the bottom row will be of excess 1. So this is how you obtain a two full word for W equals to 3. and for any h. And now to prove that it's maximal, that you cannot do better, we will just proceed by minimal counterexample with regard to h. So assume that there exists such a w that has excess 3, that is has minimal h. Then we know that both the extremal rows are forced to be full by minimal counterexample, because otherwise, if let's say the top row is not full, then that means that the top row contributes none or negatively to the excess, which means that if you strip your word of the top row, you would have also a minimal counterexample, but so that means that the earlier example would not be a minimal counterexample. So this means that both of those rows are forced to be full. So basically what we need to prove now is that that each internal row, basically all the other rows that are left, they need to be of excess 0. So first, let's assume that this row, like we assume that this row is the first, that is the first from the bottom that is not of excess 0. So if this row would be negative, then if this row would be negative, then the full word would be would have excess greater than sorry. If this row would be less than would not be full and would not be of excess 0, then it means that it would be of negative excess, which means that we would have a word of excess more than 3. But this row would contribute negatively, and we know that this word in the bottom would have would be of like we know that the first few rows from the bottom up to this new row would be of excess only 1, because all of the rows would be of excess 0 except the bottom one. This means that the factor starting from the top up to the row just above the row that we chose would be another minimal counterexample, which is impossible. So then this row, that is the first row that is not equal to 0, that is not of excess 0, is forced to be of excess 1, basically to be full. Then that means that this configuration is forced, because we know that the row below it needs to be of excess 0, which means it needs to have 2 cells. But any other configuration of 2 cell would create a cell of degree 3 in the middle here, in the middle of the top of the special row, basically. So that means that this configuration is forced. But once we have this configuration, in our project, we call this configuration a bench. And why are they important? Is because when you have a long strip of occupied cells with at both ends cells, that means that on the top of the bench, all of those cells cannot be occupied. Otherwise, they would create any cell occupied at the row above would create a cell of degree 3. So anytime we have a bench, we know that above the bench we have. I mean, we lose a lot of excess, basically. And now if we count, we know that we can see that this row is of excess -2, because it has 0 cells. So it's 0 minus 2/3 of 3, so it's 2. And we know that the cells below it has excess 1. All the cells after this have excess 0 except the final one. So basically we know that the factor from the bottom up to the empty row is has excess 0 and cis excess is additive, then we know that if the full word is of excess 3, then that means that the top factor has excess 3, but that is in contradiction with the minimal counterexample. All right, so this is just like an idea of how you can prove the maximality of an area for a fixed width. So this was like this was not like the hardest example. It's just so this was with 3, so it's like the basic case, but most of the cases look the same. It's just more tedious as it is as you go along the width, because there's more cases to check. But and also, I guess there was also as a base case the case 7 by 7, but this one you can just check it by a computer, by hand, basically. All right. So once we're done with the base cases, we need to prove for the general case. So basically, we want to prove for those cases that we can never exceed this. First of all, we need to prove that we can always reach this excess, and we also need to prove that we can never exceed this excess, and then we would be done. All right. So first of all, maybe how to verify that we can always reach the proper excess that we want. Well, we will proceed by construction. We will construct a way to always obtain for any value of h and w with the same congruence modulo 3. We will construct a way to obtain a twofold word of the right excess. So first, we start with the upper left corner tile, a 3 by 3 tile at the upper left corner. And then we tile the rest of the rectangle with this tile. And whenever we reach, let's say, so first we tile whenever it's possible. When we have the space, we tile. So we tile here, we have the space here. We don't have the space here yet, and then we have the space here. And then once you run out of space, for the borders here, we just add like a fraction of this tile that fits. So basically we just continue, but with just the first 2 columns. And we can do the same for the rest of the rectangle. And at the very end, we will have a leftover piece at the bottom corner, and then we just fill it as much as possible. So here we would add 3. And why does this always guarantee to give always the same excess, only with an excess that only depends on the congruence? Well, first of all, the first tile is always of excess 1, so this will never change. And when we tile the rest of the rectangle, this tile has excess 0. Not only that, but also so let's say any vertical slice of this tile and any horizontal slice of this tile is also of excess 0. So this slice is of excess 0, this slice is of excess 0, and the bottom slices are also of excess 0. So the only way you gain excess is at the top left corner, at the bottom right corner. And the bottom right corner will always be the same. The bottom right corner will, like the configuration of the bottom right corner will only depend on the congruence of h and w modulo 3. So this is how you get, and then for all the 6 cases, it's just then calculating the excess. But yeah, so this is how you obtain your a construction of a twofold word that has the right excess. Right now we don't know that they are twofold. I keep saying twofold word, but right now we don't know that they're twofold because we're not guaranteed that it's the maximal excess. But right now we're constructing a word that has the right excess, and we're theorizing that it is a max. Now we need to prove it. And the way to prove it is, of course, by induction, but by doing what we call strategic cuts. So for all of the 6 cases, there is a way to separate your, let's say you for all of the 6 cases, we can assume, so this is the theorized maximal excess that we have for each case of congruence. So let's say for when both H and W are equals to 0 modulo 3, then we theorize that the maximal excess is 2. So what we do is we find a minimal counterexample. We say that this counterexample is minimal with regard to any case. We say that it's just the minimal counterexample, both in H and W. And then we assume that it has excess 1 plus the maximal excess that we think. And then we cut the rectangle and we see where the contradiction lies. And I mean, all 6 cases are different, but they do not depend on the height or the width. They only depend on the congruence. So maybe we can see an example. Let's say yes, this example with when we have both H and W equal to 2 modulo 3. So basically, we have that our word W is a minimal counterexample. So it's minimal such that its XS is strictly greater than 4/3. So it's at least 7/3. And like its width is equal to a multiple of k, a multiple of 3, sorry, plus 2, and its height is also a multiple of 3 plus 2. Now we can separate its height by a height h1 that is a multiple of 3 plus 1, and its height h2, which is also a multiple of 3 plus 1. So now we have 2 rectangles. The orange, the one with the border in orange, and the one with the border in blue. We have 2 rectangles which are in the case with the width is equal to 2 modulo 3 and the height is equal to 1 modulo 3. But we know from hypothesis and also from our base cases that the excess of the first rectangle, the rectangle of the factor, basically of the orange factor, can never exceed 2/3, and that the excess, I mean, similarly for the blue factor, because both of them are in the same class, or in the same case of congruence with regard to 3. So now we have that W has excess strictly greater than 4/3, but is a concatenation of two factors that are that have excess at most 2/3, which just arithmetically does not add up. So this is one of the cases that is actually not too hard. When we look at all of the cases, the first 3 cases are cases that work just by arithmetics, like the kind of counterexample I just did. They work just by we can do a strategic cut, and then we see when we observe, okay, well, this factor and this factor, when we add them up, they cannot exceed a certain excess, which means that if our counterexample is minimal, then I mean it doesn't work, because if our counterexample is minimal, then that means that the other factors should have the right excess. But when we add their excess, they don't they can't reach the excess that we want. So this is a counterexample just by arithmetics, basically. But the bottom cases are a bit more subtle than that. What happens is that actually when we add up their excess, we can reach the excess that we want. But the problem is that in the border of those words, so usually we can reach them. So for those 2 cases, it is possible arithmetically to obtain the right excess. Let's say here would be excess 2, like 1 plus 1, so 2. Excess 2 with this configure, like with a height 4 and a height h minus 4. It would be possible. However, what happens is that if that is only possible when both of them are maximal. By maximal, I mean which means that when both of them have the maximal amount of well, basically they're twofold when they're full. And what happens is that in their border cannot match. Like this is a bit. We need more lemmas to check, but basically it's that's the phenomenon that happens. Is that yes, you can like arithmetically you can reach the excess that you want, but the problem is that both of it, in order to reach it, both of them need to be maximal. And if it's the case, then their border have to be both of their borders have too many cells with regard to the other. So yeah, so this is how you have more. So those are more interesting cases. And the last case, this one is the hardest. This one actually requires a bit even more digging than that. You need to look at the border, the borders of width 4 between those two factors. And needs another couple of lemmas. So yeah, so this is the more the nitty gritty, tedious stuff that we need to go through to prove this. But yeah, so this was done mostly by Alain Goupil. This part. All right, and now once we have this, I mean once we have all this, we have the theorem basically. So basically, what we achieve what we wanted. Basically, we have a value. You give us a value of h, w, and d, and we spit out a maximal area basically. And yeah, so this is the main result. So I guess maybe first of all, before going to the conclusion, maybe why is that interesting? I mean, so this is a good question. At first, well, I mean, at first we were interested in the problem from Alain because Alain wanted to know, he still wants to know actually, what's the for let's say we have a rectangle of a certain dimension. What is the largest snake polyomino that can fit in that rectangle? Well, so this does not answer the question fully, but it gives an upper bound because a snake polyomino is obviously a twofold. Is obviously like it's not twofold necessarily, but it is a if you look at it, like if you look at a snake polyomino inscribed in a rectangle in the context of the words that we looked, then it is a word that is in the set of words that such that no cell exceeds degree 2. So that means that the snake polyomino can never have area more than this because it's just a subcase of those words. Like it's either twofold or it's a bit less than twofold. So yeah, so this was the main reason why we looked at this problem. But yes, also maybe it can be interesting in the sense of a generalization of the dominating number problem. But this would be only for grid graphs. But basically, it gives us it gives us. So the result in the case d equals 2, it gives us the mass in graph theory. It gives us the maximal cardinality of the induced subgraph of the grid graph, such that every connected component is either a cycle or a path. So basically, what is also in another word, like you can give us like maybe for a grid, it can give us a maximal, like what's the maximal area of a forest of polyominoes, such that each polyomino is either a snake or a cycle. And like I said, it provides an upper bound for the snake polyomino of maximal area. And now maybe just to end on another note, maybe it's just so what would be the other problems to consider? I mean, so first I didn't write it there, but maybe a first for maybe a problem to seriously look at is there a cleaner way to prove all of this? Because this at the end amounted to a lot of case checking and a lot of tedious busy work, which I mean we're proud to have done, but it's 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 it, we think it could be maybe made cleaner by the use of maybe tropicals semirings. Um, if maybe we can frame this problem correctly in this framework, maybe there could be an avenue for maybe a cleaner proof. But also, I mean, at this point, we can also look at another like problem. So maybe we can look at another lattice. So now we only looked at the square lattice. So what like a 2D word, but what happens maybe when we look at 3D word? Like at this point, why not? And maybe also we used so for this problem, for the case d equals 3, we used a statistic called excess, and also I mean a similar idea on the you know, on the grid graph, on the dominating number of the grid graph also appeared over there. Like there was also a notion of excess. It was not called like that, but it was also like there was also a notion of like a certain ratio that periodically we go around, like depending on the modulo of the on the congruence of the dimensions. So for the other, like maybe for a 3D word, what would the statistic be? Would it be like I don't know? Would it be depending on the degree? Let's say so. This is a problem to look at. And maybe also another problem is okay. So now we have an object that is the two full words, like default words. Maybe we could try to enumerate the default words. So basically, so for the case equals 2, it would amount to enumerate like induce subgraph of the grid graph that such that every component is either cycle or path. So yeah, so this is pretty much yeah. So this is pretty much it. Those are the references, and thank you.
All right. Thank you very much, Louis. Does anyone have any questions? Hajime.
So thank you for that talk. And my interest is your question is so enumeration of full graph. Is it right? One of your future work is
Yeah, so, I'm sorry. What was my
yes. The third problem is
Yes,
enumeration.
that's right.
Yes, I'm interested in two full graph.
Yes.
So it generally so have many kinds of full graphs. Is it right? Or generated by one patterns or
Generated by
for symmetry or something?
yeah. I mean, of course, this. I mean, so right now it's actually so this the problem of enumeration we haven't looked at it too deep yet. Of course, the first avenue we I mean I guess we considered would be to like enumeration by maybe automatons or.
Mm.
Um, but yes, so yes, I mean I'm open to suggestion if you have them. But yes, so right now I can say that we looked at this problem too deep yet. But yes, maybe we can talk about it a bit. But yes, I have no I don't have much of an idea of how you would enumerate them right now. If that's what you were asking.
Yes. Thank you. It's difficult and so thank you.
Yes,
So
I think it would be difficult. Yes.
Are there any other questions? Yeah, Jeff.
So maybe I missed it, and maybe you already said this, but would it be of any interest to also study the problem where the connectivity also goes along the diagonal, so that you have actually, one, two, three, four, five, six, seven, eight connections?
I haven't talked about it, but it is actually also interesting. And it would basically, so in the, let's say in the graph, like in the graph framework, it would amount to looking at basically like the dominating set, like the generalization of the dominating set, but not on the grid graph, but like on the, like the two connect, like the D2 connected graph, or like the graph in which like you, like the grid graph when you're also connected to your neighbors, to like your diagonal neighbors. Yes, it would be interesting. Also, why not? It's probably that it would amount to similar proof ideas. Yeah, so like since at first we were looking at it mainly for like polyomino problems, link polyomino problems. It for us it was not really like the main, like the main focus. But yes, of course, it's I yes, of course, yes. The answer is yes. Interesting, of course.
Okay, thank you.
Are there any other questions? If not, thanks again, Louis.